Today I represent the team of Dr. Sieńko from Krakow University of Technology, Dr. Bednarski from AGH University of Science and Technology in Krakow. And I am a PhD student at Krakow University of Technology, but today I also represent the SHM System company, which is also one of the sponsors of this conference. I would like to say a few words about possibilities of application distributed fiber optic sensors for strain and temperature monitoring of early age concrete. So including the phenomena like thermal shrinkage strains and corresponding cracks or micro cracks. So first, let's answer the question what distributed sensing means. In classical conventional approach, we select one point in the structure, install the sensor, and observe what is happening with this point over time. But thanks to distributed sensing, we are able to install linear sensor and observe what is happening over entire length of structural member. We obtain distribution of measured physical quantity, so we are able to detect local events. Maybe it will be easier to imagine this process using spatial visualization. Let's consider simply supported beam. In classical approach, we select one point along the structure and observe what is happening in this specific point over time. When we want to improve the quality of our analysis, we can install more sensors and repeat this process. However, we will not be able to gain knowledge about what is happening in the structure between these points. But thanks to the distributed sensing, we can do this and observe the strain distributions in time and length domain. So we are able to identify all local events, all local defects, all local cracks. And using even a lot of spot sensors, we are not able to achieve this. So using this approach in our research, we wanted to answer the questions if there is possibility to measure directly cracks pattern, including not only locations, but also estimation of crack widths. If we are able to measure inside the concrete, not only on the surface, but without disturbing the structural behavior of concrete, because the presence of the sensor itself can somehow disturb the structural operation. And if you can measure in any direction. And I would like to answer these questions based on real case studies, real practical examples, because I think this is not only the most interesting, but also the most valuable. But the first step to answer these questions positively is to use appropriate measuring tools dedicated for these purposes. When we think about laboratory examples, we usually use optical fibers, pure optical fibers with different type of coatings, and we have to choose appropriate coating to ensure appropriate cooperation of the sensor and the measuring structure. For example, here you can see the influence of time on these coatings. When we use acrylate coating, this influence is negligible. But when we use polyamide, we will destroy the sensor itself by the alkaline concrete environment. For laboratory examples, but also in situ installations, we should use appropriate sensors, which are designed and dedicated for these purposes. And the main tasks for such sensors is to transfer strains from the concrete accurately to the sensor. And we should ensure monolithic structures. We cannot use cables with layers, with intermediate layers, which disturb this transfer. We should use high flexibility sensors, so with low elasticity modulus, so they cannot be a reinforcement for the concrete. They should be invisible to the concrete. We should use composite rather than steel or plastics, which have very limited elastic range. And when we're thinking about measurement cracks, so when we have locally very high strain values, we should be able to withstand this. And we should provide integration, good integration with the concrete by appropriate external surface. So this is the first step which we should do. And now let's move into the real case study, and let's start with laboratory examples. In the first case study, we analyzed the behavior of pre-stressed concrete slabs. Here you can see some photos from production hall from installation time. We installed two types of sensors. First is epsilon rebar, which was embedded inside the concrete along the main tendons. And these sensors were used to make measurements during early age concrete, during first days after concreting. After hardening, we installed also pure optical fibers on the surface, and it was used also for mechanical bending tests. Here you can see, maybe I should add that these sensors were installed both in the upper and lower part of these slabs. Here you can see some strain distributions in length domain and in subsequent time steps. We can observe that during the first hours, these graphs are quite smooth, and later they become more irregular because of the hardening process and occurring the microcracks. We have the lower and upper sensors, and now we can select any point along the entire length and observe what is happening with this point over time. So this is standard plot obtaining from spot point sensor, but the difference is that we have these plots in every cross section along the entire length, so we can analyze this slab not only in time domain, but also length domain. The second step was mechanical loads in laboratory in Krakow University of Technology, and some exemplary plots. Here we have 4 first load steps and compression zones, so the upper part, and tension zone, the lower part. We can see that, in fact, only in the first step, the slabs were worked with uncracked conditions. Later, we were able to identify all cracks, and what was interesting, we were able to do this even before the cracks became visible to the naked eye. So we were able to predict the places where cracks will appear during higher loads. Here you can see the same plots, but during entire research up to the destruction. So we obtained extremely large cracks, and we were able to measure it up to the failure. Another example from Leibniz Universitat in Hanover. Here we analyzed textile reinforced concrete specimens, and the optical fiber were placed directly into the concrete, but also they were glued to the textile. So making measurements during first days of hydration, we were able to obtain profiles of strains in length and time domain and compare directly what is happening in the concrete and in the textiles. We are able to analyze the interaction between these two elements. And please notice that here we used fibers with 0.2 micrometers, so it is invisible to the concrete. It doesn't influence its behavior. Another example which should be interested for those who are interested in massive structures where hydration heat plays important role. We analyzed, it was some kind of R&D research when we analyzed the behavior of concrete tube, which was equipped with optical fibers placed inside and placed in any directions. We were able to obtain the spatial visualization of strains in all directions over time. Here you can see the plot just for one section, but we have a lot of them. We analyzed both strains of concrete, but also temperature using the fibers which were placed freely inside the tubes. So they were isolated from mechanical strains. We had a lot of experiences and case studies, but I do not have time to talk about them all in details. We analyzed specimens made of reinforced concrete, pre-stressed concrete, light aggregate concrete, fiber reinforced concrete. And these specimens were different not only due to the material, but also geometry. So using appropriate composite sensors, we were able to analyze early age stage, including cracking and micro-cracking. Let's move now into the in-situ case studies, and let's start with pre-stressed concrete girders with 24-meter length. Here we installed a few epsilon rebars along the entire length and observe what is happening during early age concrete, so during hydration time. And we were able to identify all local micro cracks which appears during this process due to the constraints. But what was extremely interesting and important for designers, we made measurements also during pre-stressing and activating the dead weight of such girders. We can see that all micro cracks which appear earlier now were closed. So this was valuable information in context of durability and operation and performance of such girders, which now are operated one of the Polish production halls. Another example now from geotechnical application and slurry wall. When we made measurements after execution of such a wall, we were able to identify the strains over entire depth of such wall and identify shortening caused by thermal contraction and shrinkage. But due to the existing constraints, because of the cooperation of the slurry wall and the surrounding ground, also we were able to identify all micro cracks. Another example, which is quite similar to the previous one, is CFA concrete column. Here you can see some photos from installation process, which was quite interesting itself, but obtained results. We made measurements during heat rotation process, and results are quite similar to this previous. We analyzed shortening caused by thermal contraction and shrinkage, but also micro cracks caused by constraints. We identified also local extremes, which were related to imperfect geometry of this column. And these early age concrete measurements were later confirmed by the analysis of data from mechanical load tests, as you can see here on these plots. Another example is a 100-meter long section of highway, experimental section, which was reinforced only with composite rebars, and it was concreting along this entire length without any dilatation. So the knowledge about the crack state was extremely important for designers. Thanks to the technology of distributed fiber optic sensors, we are able to identify all local cracks over entire length, and we were able to distinguish between cracks which were very close to each other. It was possible thanks to the good integration of the sensor and the concrete, and no slippage phenomena between the concrete and the sensor, which was monolithic and has no any layers interacting with the structure. And the last example is a footbridge with a quite interesting deck. We have composite deck, which was reinforced only with composite rebars over entire 80-meter length. And here some of these reinforcements or rebars were replaced with epsilon rebars, so composite sensors with high elasticity modulus. In this case, these sensors have a double function in the structure. So there are not only the distributed sensor along the entire length, but there are also structural reinforcement. And here you can see some results in form of strain profiles over entire length in comparison with finite element analysis. These strains comes from thermal and shrinkage phase, and also from activating the dead weight of the slab. And we can see that, in fact, there is no any crack here identified, but the shape of this strain profile was caused by the static scheme and supports of the deck. Okay, let's move into conclusions. The knowledge about early age concrete cracking is extremely important, and sometimes in practice engineers are focused on cracks which coming from mechanical loads, but this early age concrete cracking is extremely important because it influences the long-term operation and durability of concrete structures, and the knowledge about them allow us for optimization both design and technology process, for example curing or pre-stressing technology, and also allows for verification standard requirements, for example, crack widths, not only on the surface, but also inside at the level of the main reinforcement. And in life and in engineering, the biggest risk is always what we do not know. And thanks to distributed fiber optic sensing, but based on appropriate composite and monolithic strain sensors, we are able to look inside the concrete without disturbing its behavior and observe phenomena which are still invisible to other measurement techniques. Thank you very much for your attention. If you have any questions, please feel free to ask or contact me directly. Thank you.